Thank you for joining me. Today we are going to do a level 4 practice problem. This one's broken up into 3 parts. If you feel lost on this one, I'd recommend going back to the level 3s or even to maybe the level 1s. All right, so let's just read the problem first. Calculate the net torque acting on the lever. Determine which direction the lever will turn, and C, provide a mass and location for a fourth mass to balance the lever. Okay, so we have a lever here, and it is ruled, which means that we have numbers and measurement values. We have 3 masses hanging with numbers on them, and there's a little note at the bottom where the problem is. It says, assume all values on masses are in kilograms. So we have a 4 kilogram, 8 kilogram, and another 4. Okay. So the first thing we're going to do is calculate the net torque. And there's a lot of formal ways to do this, but we're going to do this one a little differently. We are going to break them up, and I'm going to get the right color for this, into clockwise and counterclockwise ones. So I'm going to make a little box, and we're going to make another one here. And what we're going to do is make these ones on the left our counterclockwise ones, which are positive. So these are things that are moving this way around. And we're going to have our clockwise ones here, which are going to be negative, and those are things going in the clockwise direction. And I'm going to mark which direction which things are pulling first. So this one right here is going to pull down and around and over, so that's going to be clockwise. So I'm just going to put a little, that's where that guy is going to go. And these remaining 2 are going to be going the opposite direction. So these are going to be color-coded as such. So this means that when I calculate my torques, I'm going to put them in the appropriate boxes up above. So let's start with and I'm going to number them too. We're going to have an A, a B, and a C. So let's do A. And I want to find first what the force of gravity is for A. And that's going to be equal to the mass times acceleration of gravity. And so that's going to be 4 kilograms times 9.81 meters per second squared. 4 times 9.81. I get 39.24 newtons. Now I can calculate the torque. They're all perpendicular, so I don't need to do anything like that, anything weird. So I'm going to put it there, and it's going to be my 39.24 newtons, which looks about right. And I'm going to, let's see, get green going, because I have to determine what my displacement is, or my distance. So I'm going from here to there, so that's 50 to 5, or from 5 to 50. So if I subtract 5 from 50, I should get 45. And I'm going to put this, just because I can't imagine this thing would be that big, it should probably be 45 centimeters. So we're just going to put this as D as in cm. And that's my distance for A, but I want to convert that to meters, so that would be 0.45 meters. 0.45 meters. 17.66 Newton meters. What I'm going to do is I'm going to write that up. That's a positive, by the way, because it's in this box. 17.66 Newton meters. Okay. All right. Now, next thing to do is to start working on the other side. So I'm going to start with mass C. And I know what you're thinking, why don't you do mass B? But mass C is going to be a little easier. The reason is because it has the same mass as A, which means whatever the force of gravity for A is, C has to be the same thing. So I can start off with 39.24 newtons. And the only other thing I need to do is get the distance, which would go from 50 to 70, which is 20 centimeters, which is equal to 0.20 meters. 0.20 meters. And as a result, I get 7.848 Newton meters. And because we already determined that this is going in the counterclockwise direction, it's negative. So I can write that right here. All right. So the next one I have is for B. So I'm going to move this down a little bit, and we're going to calculate the force of gravity for B. And that's going to equal the mass, which is 8 kilograms, times the acceleration of gravity, that's 9.81 meters per second squared. And we should get twice as much of whatever the previous ones were, because twice as much mass means you get twice as much force of gravity. But we'll 81. So we get 78.48 newtons, which means now we can calculate the torque on B, which is equal to the 78.48 newtons. And we are going to multiply it. Distance between the fulcrum and where B is located, which is 10 centimeters, or 0.10 meters, 7.848 Newton meters. And because B is also going in the clockwise direction, that's going to be negative. So now I'm going to go up. Oh, that's weird. Oh, that makes sense, though. It's twice as much mass, but half the distance, so it's going to be the same as block C. So technically, I actually haven't answered a single one of the questions yet, but we're going to start answering them real quick now. So it wants the net force acting on it. So all I'm going to do is now add up all these values. So I'm going to add up the two negative 7.848, and I get, it is really eager. I should get negative 15.70 Newton meters. And this one should be positive 17.66 Newton meters. So if I combine these together, add them up, see what I get. Plus 17.66. I get positive 1.964 Newton meters, which equals my net torque. So while there's more mass, far more mass, about 3 times as much mass on the right side of the balance, since the mass for block A is so far away from the fulcrum, what we end up getting is a positive net torque value. So this first part's done. Now, determine the direction of the lever, or which way it'll turn, is really easy. primarily because we have this positive sign right here. So we can actually add that the lever is turning counterclockwise. All right. And the last one's provide a mass in a location for a fourth mass to balance the lever. So this one's pretty easy. Pretty much we can choose any distance on there and then just calculate a mass that would need to correspond to that distance, given we know that the torque we need to produce needs to be some negative version of this number. So if we need to add negative 1.964 to positive 1.964 so that they cancel out. So let's take a look. Why not do 10 centimeters? So we're going to put some block located right here, and we just need to figure out what the mass is. So we're going to call this block D. So we're going to make it capital so we can tell the difference between the direction vector and that. So I know that since I want it balanced, and we had positive 1.964 Newton meters of torque left over, I need it to be equal to negative 1.964 to cancel it out. I know my distance, which I've just determined, is going to go from here to there is 10 centimeters, or 0.10 meters. And all I need to calculate is the force of gravity. Once I get the force of gravity, I can find the mass, and I'm pretty much done. Torque equals force times distance. If I want to find the force of gravity, I'm going to divide both sides by the distance. And I get that torque divided by distance equal to the force. What we said right here, negative 1, I'm just going to leave the negative out for right now because I just used that for the direction. 1.964 Newton meters divided by 0.10 meters. The meters were canceled, and I'm left with the force, which is good. And I get 19.64 newtons. So I'm going to make that blue. 19.64 newtons. And lastly, I'm going to use Newton's second law, divided by G, get the mass. So I have 19.64 newtons divided by G, which is 9.81 meters per second squared. I get, this is kind of nice, but 2 kilograms. So the answer, so we have the answer for A, we have the answer for B, and the answer for C would be 2 kilogram mass, 0.10 meters, or 10 centimeters, not from, but to the left. Oh, actually, not to the left. It's going to be to the right, actually. And I messed up on this, and I feel really bad about that. This block that I did actually doesn't make sense to have there because we need negative. And if it's going to be negative and we're pulling, we need to be on the right side. So I'm actually adding more mass here. So to the right of the fulcrum. All right. That was a long problem, but hopefully it was worth it. Thank you very much for your time, and you have a good evening. Thank you.